Okay. Mm, two of you, yeah, I received your answers. We'll start with the discussion. So state whether the following state. So we'll be marking this as well. Okay, so make sure you're putting your marks also. State whether the following statements are true or false. The ionic radius of the following cation varies as K plus greater than calcium 2 plus, that is greater than gallium 3 plus. Now, potassium plus and calcium 2 plus are isoelectronic species. Therefore, one with the less charge will have greater radius because it has removed only one electron. And then gallium 3 plus is like down bottom the group, no? Therefore, it's like in the lowest part of the periodic table. So anyway, it will be obviously smaller than K plus and calcium 2 plus. So that is true. The van der Waals radius is one half the distance between the two equivalent bonded atoms in their most stable arrangement. Now, Van der Waals radius means, Van der Waals means it's an interaction. Now, when you have two molecules, let's say molecule A and molecule B, they have an interaction. Like it can be dipole-dipole or dipole-induced dipole, any kind of interaction. Okay, London forces. So that is what we call the van der Waals interactions. So the van der Waals radius is half the distance between the interaction, not the bonded atoms. Here you don't have bonded atoms. Here you have an interaction between two molecules. Therefore, this is false. So this can come as a covalent radius, but not the van der Waals radius. The energy for a gaseous atom to obtain an electron, that means gaining, no? Gaining an electron, always become more positive when moving down a group. Okay, now here they're talking about the electron gain energy. Now, the energy to gain an electron, no? Now, more positive means it's like becoming more endothermic, like more positive. Okay, more endothermic means you need more energy to absorb to gain an electron, but it's not like that, because when going downward the group, you know that proton number is also increasing, effective nuclear charge, those stuffs are also increasing, no? Therefore you can gain an electron. We can't say it's more positive. Okay, now across the period it is increasing, downward the group it decreases. That is the value. Okay, so yeah, this is also false. Intermolecular hydrogen bonding can be seen in para-nitrophenol. So here this is phenol. If you have studied organic, this is phenol. Then nitro group is there in the para position. So here what you can see is not intermolecular hydrogen bonding. Intermolecular means between two molecules. What you can see in para-nitrophenol is intramolecular hydrogen bonding, not inter. Intramolecular means within the molecule. Okay, this hydrogen and nitrogen can have interaction. That is intramolecular, within the same molecule, not inter. That is also false. Balmer series and the line with the longest wavelength in Lyman series give the energy line with the highest energy in the Paschen series. Balmer series and the line with longest wavelength in Lyman series. The longest wavelength is the longer transition, no? Gives the energy of the line with highest energy in Paschen series. No, that doesn't make sense. Okay, we cannot relate it to each other. That's all. So only the first one is true, other everything is false. Now here for this part it is 20 marks. Okay, 20 marks. So each 4 marks. Okay, not 2 marks, 20 marks. 4 into 5, 20. So I am moving forward. If you have any doubt, you can ask me or put in the chat box. The skeleton used to construct the Lewis structure of the anion H2XO3- is given below. X is an element belonging to the P block. Okay. XO3 minus, that means there is one minus charge. If the arrangement with minimum charges on the atom is stable, draw the most acceptable Lewis structure for this ion. Now you don't know what is X, but still with the given data and all, you have to draw the most acceptable structure. So now there should be only one minus charge, no? Now we know that oxygen can have easily minus. So one of these oxygen can have a minus charge. Then it will have three lone pairs. Now this oxygen, two lone pairs and hydrogen. Here another hydrogen. Now this oxygen we have to put a double bond. Then only we can have one minus in the structure. So this is the most acceptable Lewis structure of this compound. So for that it is 6 marks. So make sure all the lone pairs should be there. Okay, if even one is missing, you don't give the mark. To what group of the periodic table can the element X belong to? So now group is determined by number of electrons in the valence shell, no? So 1, 2, 3, 4, 5. So there are 5 electrons. Therefore, it has to belong to group 15, 2 marks. If X belong to the third period, what element could X be? That should be group 15, third period means below nitrogen, no? Phosphorus. Again, for that marks also 2 marks. Draw two other resonance structures for the above ion. So one, what you can do is this double bond you can put to the other oxygen. So that is one resonance structure. Now since you have identified, now since they didn't, we have find, now they say if X is belong to third period only, it's phosphorus. If it belong to second period, it's nitrogen. Therefore, you don't use the phosphorus symbol, okay? Still use X. So I'm putting double bond for this oxygen and this oxygen now it gets the minus charge. Okay. So this is one resonance structure. What else we can draw? So what we can do is we can have single bonds with these oxygens. Then here hydrogen, here oxygen and hydrogen. Now here you can see X has 5 electrons now, but it has shared only 4 for bonding. Then 1 electron less it has shared. Therefore X will get a positive charge. So one positive and minus get cancelled and minus remain in the structure. Now always you have to remember in the final structure there has to be one minus. Okay, you have to be noting that. Okay, until that clear, right? So based on the Lewis structure, marks for that resonance structures, each 4 mark. Okay. So here also make sure the charges are there, lone pairs are there. Okay. Otherwise, no marks. Fifth one, based on the Lewis structure given below, state the following regarding the oxygen and carbon atoms given in the table below. Okay. So O1, VACPR around the atom. Now you know there is 2 lone pairs. Therefore, that is 4. Electron pair geometry tetrahedral. Shape is angular. Hybridization sp3. Correct if X is a negative charge and both oxygen have double bonds. Okay, let's see into that. There's another structure. X and both oxygens are having double bond. So now here this atom has shared 6 electrons. 1, 2, 3, 4, 5, 6. And then getting a minus charge. Yeah, this is also possible. Now, if it is a second period, absolutely it's not possible. If it is phosphorus, but usually phosphorus doesn't get minus charge. We have not come across with structures where phosphorus have shared 6 electrons and coming a negative charge. So better we can go with the other two, okay? Yeah, it's good that you're asking. If you have any doubts, clarify now itself. Okay. So usually like halogens, we most of the time can have the ability like chlorine, it will share 8 electron, have a negative charge. It can share like 6 and have a plus charge. So but phosphorus and all we don't come up. So then filling this table, then C2 is again 4 tetrahedral sp3. C3 is 2 linear sp. C5 is 3 trigonal planar sp2. So here the marks is 16. Okay. 1 into 16, 16 marks. Next one. Identify the atomic orbitals involved in the following formation of the following pi bonds in the Lewis structure given in part 5 above. They are asking the pi bonds. Huh? Now you know that hybrid orbitals are not forming pi bonds. The atomic orbitals only involved in the formation of pi bond. C3 and C4. You can see it's second period no 2p 2p. Then C5 and C6 2p 2p. Marks for which one? The table 16 marks. A part 4 into 5 20 marks. B part Lewis structure 6 marks. The period 2 marks. Element 2 marks. Resonance structures each 4 marks. Table 16. Then the pi bonds 4 marks. Okay. Each 1 mark into 4. Identify the atomic or hybrid orbitals involving in the formation of the following sigma bonds in the Lewis structure given in part 5 above. Okay, now hydrogen 1 is sp3. Here sp3, sp2. No, sp3. Then sp3, sp. Then sp, sp2. Then c6. C6 is sp2. sp2 3p. Okay, chlorine is 3p. So what comes is the final shell only involving in the bond formation. No? So final shell of the element only we take chlorine as 3p. But chlorine, now it has 3 lone pairs. No, that means 4 VsPr pairs. Then you can write it sp3 also, no problem for sigma bonds. 3PO, sp3, they give marks. Then approximate marks for that is 1. Each 1 marks 10 marks. Okay. What is the approximate value of the bond angle around the atom C5 in the Lewis structure given in part 5 above? Around C5 atom. Okay. C5 you can see that's trigonal plane of 120 degrees. For that 2 marks. Now usually in the schemes like they give a range. Now here 118 to 122. In this range if you have written they'll give the marks. So 120 is the ideal one. Okay. For that marks is 2. This 2 marks for that. Until that all clear? Any doubt? The dipole moment of lithium hydride is 1.964 into 10 power minus 29 coulomb meters. If the bond length of lithium hydride is 1.596 into 10 power minus, find the percentage ionic character. Now here you have to use two equations. Now you know that dipole moment is equal to charge of the pole, charge of that molecule pole, okay, into the bond length. Now dipole moment and bond length is given. That means you can find the charge of the pole by substituting for that equation. Then if you find that, then what you have to do is you have to find the percentage of the ionic character. So percentage ionic character is calculated as charge, that charge pole, okay. Mm, Give me one second. Okay, we'll continue. So they have given the dipole moment and the bond length. So first you have to substitute and find the charge of the pole or partial charge of the molecule. Then charge of that over charge of the electron, okay, into 100% will give you the percentage ionic character. So here dipole moment is 1.964 into 10 to the power minus 29. So that if you divide by 1.596 into 10 to the power minus 10 will give you the charge. So here 10 to the power minus 9 on top. So 1.964 divided by 1.596. The answer would be 1.964 divided by 1.596. 1.231. Okay. 1.231 into 10 power minus 9. Okay, that's the charge. 1.231 into 10 power minus 9. That you have to divide by the charge of electron. 1.602 into 10 power minus 19 and multiply by 100. So your answer would be 0.768 here, that division, times. Here you will have 10 to the power minus 10 on bottom. If you take it on top, 10 to the power, this is 29, right? Okay, I took it as 19. Okay, here 10 power minus 20. Yeah, 10 to the power minus 20 here. And below you have 10 power minus 19. Then it becomes 10 power minus 1. So, wait, I'll write it clearly. 1.964 into 10 to the power minus 29 divided by 1.596 into 10 to the power minus 10. So here 10 goes, it becomes 10 to the power minus 19. Okay. So here 10 to the power minus 19. Then that both cancel. And you multiply by 100, no, 76.8%. Now clear? Anybody got this? 76.84. Anyone? Others? So if you write the equation and substitute also, sometimes you will have marks. So here for the substitution with units is 2 marks. Okay, for the first part. Finding the partial charge, substitution with the unit, you have 2 marks. And then, so how much is the remaining marks? Until that 50 and here 30. Then 89, 30. Okay, for these 30 marks, then 20 means here it has to be 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. For the ionic charge part, okay, for the substitutions, you have 6 marks and then final percentage 2 marks. So altogether 10 marks for the C Roman number 1. Okay. So when you're substituting, you have to substitute with the unit. Otherwise, that substitution marks you won't get. So see, if you don't, for the final answer, only 2 marks. But if you have just substituted, you get the marks for the equation including that. Next part is arrange the following in increasing order of the property indicated in the parenthesis. So here it's carrying 20 marks, each 5 marks. Yeah, 5 times 4, 20. Now metallic bond strength. So metallic bond strength is depending on some few factors. One is the number of electrons it is delocalizing. Okay. Then the charge. After that, the size. So if you have more electrons delocalized, more electrons involved in bonding, metallic bond strength will be stronger. If you have greater charge also, it will be stronger. And if you have a smaller size, it will be stronger. Okay. Now we will think about this. Metallic bond strength. Now sodium and potassium, you can see they are in the same group now. So when you, now they don't have a charge also. Now when they have the same charge, if you take the charge of the metal, sodium plus and potassium plus. So when you go downward the group, potassium's size is increasing. If its size is increasing, metallic bond strength will be less. Okay, so potassium's metallic bond strength is less than sodium. Now, when you take sodium and magnesium, they are in the same period. Now, magnesium has smaller size and also greater charge when compared to then sodium. Magnesium has greater metallic bond strength than sodium. Then obviously it's greater than potassium also. Manganese, if you take, that's a D block element. So D block elements are giving delocalizing lot of electrons for bonding. Now, you know, manganese oxidation number also +7 and very smaller size compared to all three. So it will have the highest metallic bond strength. Next highest is magnesium, then sodium, lowest is potassium. So these are the 3 criteria you have to follow for metallic bond strength. It will come for the metals. Then next you have to see the bond length. Now then if you want to see the bond length, first just draw it. NH2 OH, NO bond length. Then NO. NO would be, if you put a triple, NO has a odd electron. NO has a double bond and it has a odd electron, okay? Then NO2 minus is like this. Then next one, NO2 minus, then NO3 minus, it's having 3 bonds now, plus, minus, minus. So now let's see. Now here you can see NO double bond. It will not change. No, it will not change. Now here NO single bond. So that will be the longest. Okay, single bond is always longest. Then you can see here it's a fixed double bond. Other 2 structures you can see the double bond can change. Okay, now here double bond can change into 2 locations. In NO3 minus double bond can change into 3 locations. So they are, the resonance structures are there. So now here you can see NO is having a double bond. So that will be the lowest. Now, if you have more resonance structures, I told you that bond lengths become larger. Now, NO3 minus double bond go for 3 places. Therefore, it's dividing into 3. Then it will be more longer. Okay. Because the double bond nature is reducing now. And here it is NO2 minus. So simple fact is like if the double bond is like going for more places, the bond will become larger. Bond length becomes larger because double bond is dividing more. Then its double bond nature decreases and it gain more single bond nature. Then more longer. Okay. So NO3 minus greater than NO2 minus. Next one is second ionization energy. Fluorine, oxygen, nitrogen and neon. Fluorine, nitrogen, oxygen and neon. So when you take the, first we'll draw the first ionization pattern. So lithium, beryllium, boron, then carbon, nitrogen, oxygen, fluorine and neon. So neon is here, fluorine is here, nitrogen, oxygen. Now second ionization energy means we have to shift the locations. Nitrogen comes here, oxygen comes here, fluorine is here, neon is here. Still neon is largest. Next is oxygen. After that fluorine, after that nitrogen. That is the second ionization energy. Now next one is decomposition temperature. Now decomposition temperature if you take, now here you can see sodium nitrate, potassium nitrate, magnesium nitrate. Now sodium and magnesium nitrate if you take, I'm comparing that to, you can see that their anion is the same, NO3 minus, but the cation is different. You have Na plus and magnesium 2 plus. Then you have K plus also. All of these, the anion is same, but the cation is smaller. Sorry, cation is different. Okay. Now we'll see sodium plus and potassium plus. Now they are polarizing power of the cation, depend on the charge and size. Both have the same charge. Then it depend on the size. So smaller size will have, now here they are talking about what? Decomposition temperature. Okay. Charge is the same. Yeah, smaller size is having greater polarizing power. Yes. Then greater covalent nature, lowest ionic nature, and you have the lowest decomposition temperature. Yeah. Then if you take sodium plus and magnesium 2 plus, their charges are different. So magnesium 2 plus has a greater charge. So if it has greater charge, then it has greater polarizing power, no? Then greater covalent nature, lower ionic nature. Then decomposition temperature is less. Hold on, now we will have to analyze this because it's not in the same period or same group. Now, obviously, ammonium nitrate only will be the lowest. Okay, now because others are strong ionic compounds, now when compared to ammonium nitrate, because they are having metals as the cation. So, ammonium nitrate has to be the smallest. Then we have to analyze the magnesium, potassium, and the sodium. So, here we'll take sodium and potassium as a comparison because they are in the same group. Then later we can see sodium and magnesium because they are in the same period. Wait, I'll screenshot. Now we have sodium plus and potassium plus. So this is depending on the polarizing power of the cation. So polarizing power of the cation is depending on the charge and size. Higher charge and lower size will have higher polarizing power. Potassium is having, now both of them have the same charge. Now therefore it depends on the size. Now potassium has greater size. Okay. Therefore its polarizing power is less. Covalent nature is less and ionic nature is greater. So K plus has greater ionic nature than sodium plus. Okay, now that is done. Greater ionic nature means greater decomposition temperature. Now sodium plus and magnesium 2 plus will take. Now you can see magnesium 2 plus has greater charge and smaller size as well. Therefore, it has higher polarizing power, higher covalent nature, lower ionic nature. Okay, lower ionic nature, then lower decomposition temperature. So, sodium plus is more ionic than magnesium 2 plus. K plus is greater than sodium plus. So, you can understand the highest one is K plus, right? Potassium nitrate because it has the highest ionic nature. Next, sodium nitrate. Next comes the magnesium nitrate. So these has metals as the cations. No, they will form strong ionic compounds. So that is why I put ammonium nitrate having the lowest decomposition temperature. Is that clear? So each 5 marks, 5 into 4, 20 marks for this Roman number 2. And now I want you to tell me the marks out of 100. So out of 100, tell me how much you got, okay? True or false, it is each 4 mark. Hold on. Each 4 mark, yeah. Last question. No, last question, your order has to be correct. Perfect. Like this entire order has to be correct to give marks. If this order is correct only, you get 4 marks. Even 1 if you have interchange, that's wrong. Okay, others who didn't put the marks, just add and tell me the marks. Everyone clear, right? If you have any doubt, you can ask. So usually first structure is the easiest. So try to take above 75 for that. Okay, then your marks will balance. Now we'll go to the second structure so that you know it. The second structure is always inorganic. So second structure is also very easy. No any calculation. No need to think much. You just have to identify the element if you are very thorough with inorganic. Now you know these are compulsory questions. X, Y, and Z are three consecutive elements with atomic numbers less than 20. One of them exists as a gas at room temperature. They are consecutive, one after the other. Out of the oxide with the highest oxidation numbers, the oxides of Y and Z react with water, giving strong acids, while oxide of the X is giving a weak acid. So the oxides are reacting with water and giving strong acids. So now here we have to identify X, Y, and Z. Now here the oxides are reacting with water and giving strong acid. So that's a very good point to identify the element. So this should be the third period non-metals. Now usually non-metallic oxides now are acidic no. So non-metallic oxides are acidic. So those oxides if they react with water they can form strong acid. So X, Y, Z should be non-metals and they should be one after the other. So now here you can see Y and Z oxides are reacting with water and giving strong acid. But X is giving a weak acid. So it can be in the order of phosphorus, sulfur and chlorine. Okay. So X has to be phosphor because phosphoric acid is weak. Then sulfur, you know, sulfur trioxide can react with water and give sulfuric acid, which is a very strong acid. Then next one, chlorine is giving a lot of strong acids like HClO4, HClO3. Okay. So these are the elements. Write down the reaction of the oxides with the highest oxidation number with what? So now here you have to write the oxide. Now they can form oxides with different oxidation numbers. Okay. Now phosphorus forms the highest oxidation number +5, P2O5. Sulfur forms sulfur trioxide. Okay. Oxidation number +6. Chlorine is forming +7 oxidation state, Cl2O7. So these are their oxides with highest oxidation number. Now sulfur can form another oxide also, sulfur dioxide SO2, but oxidation number is +4. Here they are recording the highest. Then oxides are reacting with water. So these we have studied. Under each one we have studied about how oxides are reacting with water. So P2O5 with water is forming H3PO4, 2H3PO4. Okay, now it has to be balanced as well. Then sulfur trioxide with water is forming sulfuric acid H2SO4. Then Cl2O7 with water is forming the strongest acid HClO4. I hope it's clear. The marks. Okay, for the identification 15 marks, each 5 mark. Okay, each 5 mark. Then for the balanced reactions, 4 into 3, 12 marks. 4 into 3, 12 marks. Then write the reaction of Z2, that is Cl2 with cold dilute NaOH. So this is cold, okay, not hot. Cl2 with cold dilute NaOH, that's also a very frequent reaction. Forming NaCl is coming with both cold and hot. NaCl comes. With cold, that is NaOCl. With hot, NaOCl3. And then water also. 2 sodium hydroxide and it will be water. No, you have to answer as Cl2 because we identified no, what is Z. Therefore, now you can use the real symbol. Which of the products in part 3 above show bleaching property? Now, you know OCl minus in NaOCl can show bleaching property. Okay, NaOCl. But now bleaching properties are removed from the syllabus. Okay, like old papers like before 2021, like and all, you have to know about the elements bleaching properties. But now you no need to know that. Okay. Next. But you have to remember that disinfectant. You remember when NCl3 reacted with water is forming HOCl, which is used as a disinfectant. That you have to remember. That's not a bleaching property. That's a disinfectant. But here NaOCl has bleaching property. So the marks for this, 4 marks for this reaction. For the bleaching property identification, 3. So put the marks and go. Show how the product behave as bleaching agent by means of chemical reaction. So what happens is that when NaOCl, okay, it can make the bleached property like flower petals and all, it can be bleach. Okay, so what happens is NaOCl will get converted to sodium chloride and oxygen. And oxygen. So these 2 and 2. So oxygen will do the bleaching property. Give reactions. Give reaction to show how Y behaves in each of the following cases. Y is sulfur. Sulfur should act as a oxidizing agent. Oxidizing agent means it should undergo reduction, no? Sulfide formations you can write, no? Sulfur with sodium or magnesium forms what? Magnesium sulfide. So here sulfur is 0 and going to -2. Can you see reduction? Undergoing reduction is an oxidizing agent. Then reducing agent. Reducing agent means sulfur has to undergo oxidation. Oxidation of sulfur. Anyone wrote it? Oxidation of sulfur. So we can take an oxide formation, right? Now sulfur reacting with oxygen and form sulfur dioxide. So here 0 going for +4. So that is it can act as a reducing agent. But here, hold on. Now if it is undergoing a reducing agent, something else should reduce now. We can't take it. Here we have to write redox equation. Sulfur with anyone wrote sulfur acting as a reducing agent? Yeah, that's the issue now. If we take a sulfur containing compound, then we can write. No? The thing is with element sulfur only it's difficult. Now first one is okay. Then sulfur containing, we'll go with the sulfur containing compound because with element it's difficult. Okay. So we'll take sulfur dioxide with MnO4 minus or something. So sulfur dioxide here it's +4. Sulfur is +4 and it will oxidize to SO3 +6 and MnO4 minus will reduce to Mn2 plus. Now here +7 going to +2, that's -5. So here +2 +4 is going for +6, that's +2. So 2 times 5, then here 5 times 2. 2 and 2. So we'll work it out as the acidic medium. So this side -2 charge, that side +4 charge. Then we can put here 6H plus this side. Then here 18 oxygen. This side 15 oxygen. You have to put 3 water. 3 water means 6 hydrogens are coming. So we'll go with the sulfur containing compound. Okay, with sulfur alone, it's difficult. We don't have a reaction. So the marks for these 6 marks, this one each 4 mark. Okay. Give the balanced chemical equation for the reaction of Z with water. What is Z? That is chlorine. Okay, chlorine with water, that's actually Cl2. Okay, Cl2 with water is a disproportionation reaction, a very frequent one. It is forming HCl and HOCl. Okay, disproportionation reaction. Draw a rough diagram to show the variation of the boiling point of the hydrides in the group to which Z belongs. So that's group 17, no? HF, HCl, then you have HBr and HI. So you remember I gave you the boiling point graph. So I hope you remember. So here HF will be the highest. HCl, then we have HBr, HI. Now you know why HF is boiling point is highest, right? Because it has hydrogen bonding. Strong interaction, no? Therefore it has stronger boiling point. And if you take HCl, HBr, HI, all of them are having dipole-dipole interactions. So boiling point is depending on the molar mass. So HI has greater molar mass, greater boiling point. Next greater molar mass is HBr, then HCl. That's how it comes, okay? So HI has to be lower than HF when you're drawing that curve. So that graph, it is, for the shape you have 4 marks. Okay, for the shape you have 4 marks. Axis now you have to mark. This is the boiling point axis. Okay, y-axis is the boiling point. For the axis 2 marks. Then for the compounds, naming the compounds, another 2 marks. Then 8 marks. Until that, is that clear? I'm going to the next part. If you have any doubt, just drop to the chat box. X and Y are 2 water-soluble salts. The following tests are carried out to identify X and Y. Okay. Added dilute HCl to X. A gas with pungent smell was evolved. Now they are salts. Okay. Now X and Y are salts. No, so they are compounds. Added dilute HCl to X. A gas with pungent smell is coming, and also yellow turbidity. Then probably like sulfur has to like form. Okay, let's see to that. X and Y are now mixed together. So a precipitate and a solution is forming. Only when A was heated, a black precipitate and a colorless gas was obtained. So that gas is an acidic gas. Okay. So when you heat it, you are getting a black precipitate. Okay. So heated being black means, you remember we had lead thiosulfate, silver thiosulfate. When you heat, they give black precipitates. Okay, that's a point. Let's see. Solution B is heated in the presence of aluminum in basic medium, a gas with pungent smell which is turning red litmus blue. That means ammonia gas is released. When you put aluminum in basic medium, so you remember that is the test for identification of NO3 minus. That means in solution B, NO3 minus is there. Added dilute H2SO4 to B. No observation was noted. So they put an acid, no any observation. X is subject to flame test, yellowish color. So flame test yellowish color means it is sodium, right? Yeah, it is sodium. So sodium means X is having sodium. Now we found out. Now both X and Y Our compounds, no, it should have a cation and anion. Y also should have a cation and anion. Now, so X, the cation is sodium. Now we found out that. Now they are adding dilute acid to X. It is giving a gas with pungent smell. So here I said yellow turbidity. That is sulfur. Pungent smell gas is sulfur dioxide. So this characteristic observation is coming when dilute acid is added to S2O3 2-. I gave this in the identification also of thiosulfate ion. When you put an acid, it gives sulfur and sulfur dioxide. That means in X, the anion is this. Cation is sodium. So what's the compound? Sodium thiosulfate. Anybody got this? Anyone who identified? So whenever they give compound, if it is a salt, then you have to identify that has a cation and anion. Then those both cation and anion will have observations. So we can see the anion S2O3 2- gives sulfur and sulfur dioxide in the acidic medium, and X giving the flame test yellowish color. So that's sodium thiosulfate. Now we have to find Y. Now when X and Y are mixed together, a precipitate is coming and a solution B is obtaining. So that precipitate, if you heat it, it is turning black. So when heated turning black, we have two. Either it can be silver thiosulfate or lead thiosulfate. So mostly now here heated turning black means lead thiosulfate, because silver thiosulfate is turning black on standing, not when heated. So lead thiosulfate means the cation in Y is lead. It has lead. Then only that lead can react with the S2O3 2- of the X. Then we identified that it has NO3- to the solution B. That means the anion of the compound Y is NO3-. Therefore, Y is lead nitrate. Understood? So you have to relate all the identifications, okay? So when you do a lot of inorganic questions, quickly you will grab. Just one point is enough to identify, okay? So each 5 mark for the identification. 5 for this and 5 for this. Now you have to identify rest of the things. What is A? A is lead thiosulfate. Then P is sulfur dioxide. R, ammonia, pungent smell gas. D, lead sulfide. Then Q, colorless gas, that is sulfur trioxide. So that is when lead thiosulfate is heated, okay? So in reaction 3, the reactions taking place in 3 and 4. In 3, they are heating A, no? That means lead thiosulfate is heated. It is giving you lead sulfide and sulfur trioxide. So I have given that already. Then 4. 4, what happens? NO3- is reacting with, that's also a very frequent reaction in redox. Aluminium goes to AlO2-. NO3- is going for ammonia. Then here +5 going to -3. Here +3, 0 is going to +3. So here +3. 3 into 8 means here 8 and 5. 8 and 5. So here you have -8 charge. Here -5 charge. Then you have to put 3 OH- here. In oxygens, if you take 5 3s are 15, here 18 oxygens. This side 16 oxygen. You have to put 2 water here. Is that okay? Balanced here -5 -8. So we have put 3 OH-. 5 3s are 15, 16, 17. Okay, here 18 oxygens. 8 2s are 16 oxygens. Then you need 2 more oxygens, okay? Then 5 3s are 9. 9 and 4, 14 hydrogen. Oh, hydrogen is not balancing now. Where did we go wrong? Wait, let me balance that again. So aluminium is reacting with NO3 minus and giving AlO2 minus and ammonia. So here 0 plus 3. 3 times 8 here, here 5, here 8 and 5. Okay. Then here we have minus 5 charge, here minus 8 charge. Here 3, okay, here 3, no, not 5, it's 3. Aluminium, NO3 minus, ammonia, and AlO2 minus. So here 8, 3, 3 and 8. Okay, here minus 3, here minus 8. Then we have to put 5 OH minus. Then it's balanced. Then we have 5 oxygen, 9 oxygen, 14 oxygen this side. Here we have 16 oxygen, so we have to put 2 water this side. Then it's balanced. Okay. So, that is okay. Yeah, with that it's over. 10 mark. Each 5 mark. Okay, each reaction 5 mark. So now you calculate and tell me. Then Roman number 2, the marks is each 4 mark. Okay, so 4 into 5, 20. Each A, P, R, D, Q, each 4 marks. Okay. Now everyone just send me your corrected answers and in 5 minutes we'll start the organic revision. Okay, we'll start now. Okay, so last class I revised the organic naming, right? Did you all go through it? Now we'll do some few past paper questions. Okay. So I hope you all went through it again and all. And then we can go with the isomers and stuff. Okay. Yeah. Now start 3 and 4 quickly. Okay. 3 and 4, just pick the answer and put to the chat box. Okay, 3 and 4 both together, put me the answer. Okay, others. Only one respond I got. The IUPAC name of the compound. Now what you should do first, you have to choose the longest carbon chain including the main functional group. Here you can see that's carboxylic acid. And your main chain should include the double triple bonds also. Okay. So now look at this. This is the longest carbon chain. And you know this carbon only we start numbering. 1, 2, 3, 4, 5, 6. So here you can see in the fourth carbon we have a propyl group. Here 3 carbon, no? So this is a propyl group. In the fifth carbon you have a bromine group. So 5 bromo, 4 propyl. That's how it has to start. Now here bromo and propyl. They are all substituent groups now. Then you have to go with the alphabetical order. So bromo is B first. So 5 bromo, 4 propyl. Then how many carbons in the main chain? 6. Then hex. And there is a double bond in the fourth carbon. So 5 bromo, 4 propyl, 4 hexene. 4 hexene in is representing double bond. 4 hexene is representing the double bond is in the fourth carbon. And oic acid because of the carboxylic acid. That's how you name it, okay? Then the fourth one. So fourth one also now you can see carboxylic acid is there. Then you have to take this chain because it has the double bonds and the carboxylic acid. Then here 1. Then you can see second carbon has bromo. 2, 3, fourth carbon has a propyl group. Fifth carbon has a chlorine group and fourth carbon has the double bond. Now bromo, chloro, propyl. B only should come first. Bromo. 2 bromo. Then 5 chloro. 4 propyl. Then in the main chain we have 1, 2, 3, 4, 5, 6, 7. Then heptanoic acid. Second one. So both 2. Okay. 2 bromo, 5 chloro, 4 propyl, 4 heptanoic acid. 4 heptene, that is in the fourth carbon you have the double bond and the hept is telling there's 7 carbons in the chain. Oic acid is a carboxylic acid. Is that clear now? So always you will have one MCQ from the naming. Okay. So this fifth one like you won't have, okay, the benzene and stuff. Go to a newer one. Yeah, now 24, 25, 26. Everyone has to put me the answer. Now try the 24, 25 and 26. All of you has to put the answer. Even it's wrong, it's fine. You try and tell the answer, okay? Okay, done. Put your answers to the chat box. 24, 25, 26. You have to be quick. Everyone have to put. Two people had sent me for few. Okay, we'll start with the 24th one. What is the IUPAC name of the following compound? So we can see here there's a aldehyde group. So that is the main functional group. Okay, therefore you have to take the chain, including that group and the triple. Then you have to number the carbon chain so that the main functional group gets the lowest number. So we start numbering from here. 1, 2, 3, 4, 5, 6. Then you can see third carbon only has the aldehyde. Then fourth carbon has OH. Now OH we call it as hydroxy. Okay. Yeah. It has to be 4 hydroxy, right? Mm. Oh, we start with the aldehyde? No. Aldehyde usually comes in the corner. Okay, the chain is this. This is the chain. So aldehyde, it's always in the corner carbon. So 1, 2, 3, 4, 5. So third carbon, we have the alcohol. So 3 hydroxy, 4 ethyl. It can't be 4 ethyl, right? Yeah, we start numbering from the aldehyde. Isn't it 2 ethyl? Yeah, 2 ethyl, 3 hydroxy. Ethyl first, 3 hydroxy. Pent 4 ine. 1, 2, 3, 4. Yeah. So pent 4 ine and al. Fifth one, no? 24, fifth one. Then 25. What is the IUPAC name of the compound shown below? Okay, now here we can see a carboxylic acid. So this is the chain. 1, 2, 3. Third carbon you have nitro. Fourth carbon bromo. So 4 bromo, 3 nitro. Then second carbon has the double bond. Hexenoic acid. Second one is the correct one because you have to keep a space between acid and hexenoid. So the first one, no space. 25, 2. 24, 5. 26. What is the IUPAC name of the following compound? Now here you can see there's a ketone group here, alcohol and amine group. So you know ketone. Aldehyde, ketone and alcohol. That's how it goes. Then, mm, so ketone will be the main functional group. So here 1, 2. Second carbon has the ketone. First carbon has the amino group. No? So 1 amino, 5 hydroxy. That's how it has to come. And there's 5 carbons in the main chain, then pent. In the second carbon, we have the ketone, so 2 pentanone. Third one, 1 amino 5 hydroxy, 2 pentanone. Okay, is that clear, everyone? Okay, now we'll take some newest ones. Hold on. So this year paper. Seventh question. Tell me the answer. Okay. So this is the main chain, right? Probably. So we have an aldehyde, that's the main functional group. So one, two, three. So we can see in the second carbon we have methyl, third carbon chloro, fourth carbon has the triple bond. So 4, 5, 6 hex. 2 methyl chloro, 4 hexyl. Yeah. So now here, methyl and chloro, if you take the alphabetic order, you have to follow. It has to be 3 chloro first and methyl. So fifth answer, okay? Okay, right? Okay. So I hope you're okay with naming. So after naming, what we come is for the concept of isomers. So from isomers, you have one whole structure. Okay, you have one whole structure, they say. So isomers is one of the important like concept you have to learn in organic, apart from the conversion. So there's basically there are like structural isomers and stereoisomers. Structural, there are like three types: chain isomers, position, and functional group. So let's see the structural isomers. Okay. So isomers. Now, what do you mean by isomers? Is like different structures. Okay. The same. That means the compound is the same, but like different orientation of the same compound. That way we can say. Okay, now we are going to talk about structural ones. Structural isomers. Now, structural isomers, there are three types: chain isomers, position, and functional group. So, what we mainly use is the chain ones and the position ones. Okay. Now, let's see what is chain isomers. So here what happened is the chain only will change. Now there's a carbon chain now in any compound, there's a main carbon chain. If you're like changing the main carbon chain, we call it as the chain isomer. Okay. Now look at this. Now I will draw a simplest one. So here you can see this is a 4 carbon chain compound. Okay, 4 carbon chain compound. I'll draw it like. Okay. So all of these are having hydrogens. Okay, will form four bonds. So this is a four carbon chain compound. Now this same compound I can draw as this way. So what I'm going to do is this carbon I'm going to branch it and put it here. Look at that. So now here. Look at this. So here four carbon chain compound. Now it has become a three carbon chain compound with a methyl group. So these are isomers for each other. Okay. These are only we call isomers. So here the molecular formula, everything will be the same. The thing is nature of the chain will alter. Now this one had four carbons. Okay, this chain had four carbons. Now the main carbon chain is having only three carbons. And in the second carbon you have a methyl group. So this is how you draw isomers. Okay. Now let's take a five carbon chain. Okay. Five carbon chain. So all of them will have hydrogens like this. Now we can branch one carbon. I'll put this to here. Then it becomes like this. This is isomer. Then what we can do? I can branch another one. I can put this carbon here also now. Then like this. So these are all isomers to each other. Okay, molecular formula is same, but you can see the chain has changed. Now here five carbon chain, here four carbon chain, three carbon chain. So if the carbon chains has changed, then we call it them as chain isomers. Did you all understand that? Just take a quick note. Note down and raise hand. Okay, now I'm giving you a six carbon chain compound. I want you to draw the all isomers for that. Okay, this one. A six carbon chain compound I have given. Now draw the isomers. Chain isomers only I want you to draw. Okay, that means the main carbon chain has to change. But still the total carbon number has to be 6. Okay, it can't be changed. Okay, did you all draw it? So what you can do, you can branch this here, then it becomes like this. So see, there's only 6 carbons. So now here I have only 5 carbons in the main chain. Now I can branch another one also. I can bring this here. Then it becomes like this. Okay. Then I can also put this here. There are different forms. Okay. Here carbon. Here another carbon. Here this way you can get. Then you can also get like this. Mm, no, that's the same thing. Okay, so these are the different forms. Okay. Did you all get that? So you should be able to like the same. You have to like draw different chains. Okay, here 6 carbon, here 5 carbon, here 4 carbon. Okay, 3 carbon chain can we? No, right? I don't think we can. Yeah, because six, no. So did you all understand chain isomers? I'm just introducing the chain isomers. So likewise, you can take chain compounds and then practice. Okay, practice drawing different forms. You should be able to draw that quickly. Then only you can draw all the possible structures in the organic structure and then find the correct one. No, no, it's not like that. No, it depends. Like now here you can see there is 6 carbons. No, then you have now you can change the main chain. Now here the main chain has 6 carbon. If you want to make it 5 chain, then you have to branch one. So I'm putting the carbon to this carbon means. Now here you can see this is the main chain. Here 5 carbon. This is the main chain 5 carbon, and in the second carbon you have a methyl group. Earlier one it's a full linear 6 carbon chain. So these are this is another isomer of that. Then I can also branch another carbon. I can put this carbon here as a branch and then make it a 4 carbon. Then here CH3 group you will have. Here also you will have a CH3 group. So that's another isomer. Okay. Yes. Then what else? What we can do is I can put this group here for this one. Then it becomes. So make sure your structure should be different. Okay. So here still now you can see here 4 carbon chain, but one carbon has the 2 methyl groups. The second carbon has the 2 methyl groups. But in the previous one you can see that's also a 4 carbon chain, but second carbon and third carbon has the each of the methyl. So I hope you're spotting the differences. Okay. So these are chain isomers. Now you see the last one. Last one both are same, having the same chain, but you can see the methyl groups are in different locations. So that's the next one we are learning, position isomers, where we change the position of the substituent groups. Okay. Now is it clear? So I'll put the position isomer now. Position isomer means what happens is carbon chain remain constant. Okay. Carbon chain is the same. Chain will not change. But the position of the substituent groups like alcohol groups, methyl groups, okay, those like halides, those positions will change. Now look at this example. So here you have a OH group. Now first carbon is having the OH group. Okay, now I'll number the carbons 1, 2, 3, 4. First carbon has the OH group. Now I can also put this OH to the second carbon. Then that's another isomer. Okay. Okay. Second carbon has the OH now. Now let's say the OH is here. Now the OH is here. Tell me the OH is in the second carbon or third carbon. Answer me. My third structure. Tell me whether OH is in the second carbon or third carbon. Yeah, it's in the second carbon because always we number the chain. Okay, we are numbering the chain such that the substituent, the carbon with the main functional group should get the lowest number. Now here we number it 1, 2, 3, 4. Now here we have to number starting from here. 1, 2, 3, 4. Then only the carbon with the main functional group will get the lowest number. So that's still in the second carbon. So can you say 2 and 3 are isomers? They are not isomers. They are the same compound. So 1 and 2 is a isomer. Okay, 2 and 3 are the same thing. Okay, not isomers. So I hope you spot the difference. So that is what we called as the position isomer. Okay. So next week we'll be working out questions on isomers. So I'm introducing you the chain isomer and position isomer. So make sure this week you practice. Okay, more on the chain and position isomer. So note that down. So while you are noting, I am putting you the functional group isomer. So that's not like coming in the questions, but you should know it. Functional group isomer means like two functional groups. Now here what happens is molecular formula is same, but it will have two different functional groups, but those functional groups are isomers. The pairs are like alcohol and ether. Alcohol and ether. Now we'll take the molecular formula. Look at this C2H6O. This is the molecular formula. Now that's how in the structure they will give the molecular formula. You have to find the organic structure. So I'll draw the alcohol. CH3CH2O. So this is the alcohol for the molecular formula C2H6O. I can also draw an ether compound. You know, ether, you will have two alkyl groups on either side of oxygen. So you can see for the same molecular formula, I can draw an alcohol as well as an ether. Therefore, these are isomers. Okay, alcohol and ether are functional group isomers. Now you can see the molecule structure is a bit different, but still they are isomers. Okay. Then likewise, we have another pair also. Aldehyde ketone are also functional group isomers. Now look at this. We'll take the molecular formula C3H6O. Now for this molecular formula, I can draw an aldehyde. CH3CH2 C double bond OH. Here CH3 C double bond OH. Then we also have carboxylic acid ester. Okay, these are the functional group isomers, but usually these, of course, haven't come for questions, but you have to remember. Not all of these. And when you're done, raise hand. Okay, done. Others? Okay. So all the three isomers are like introduced for you. So now next class we will learn how to apply them for questions, and yeah, after that conversions will come. So we have to learn conversions and only come back for the past papers. Okay, I'll keep it for a while. So I hope you all are on process. Now some have finished learning organic, some are on the process of learning. So yeah, so I hope you will be able to catch it up very soon. Yeah, so those who have note down, you all can leave.